Section 7.7 is called complex numbers. Complex doesn't mean hard, it just means a different type of number. So in general, we have numbers. I say numbers in general. Any kind of digit you could put together, like let's say -3 or 1/2 pi, square root of -2, 0.23 repeating. Any kind of combination of digits we can classify as a number. From there, we have two different types of numbers. We have what are called real numbers, and we have what are called imaginary numbers. The combination of these two is called a complex number. So a complex number includes a real number and an imaginary number. Imaginary number would be what you get when you take the square root of a negative, the square root of -1, the square root of -4, square root of -20. Any kind of square roots of negative numbers is called imaginary. Everything else is a real number. You could have a real number like 5 is a really good real number. So it's -5, or 1/5, or pi, or the square root of 3. Complex number is generally written in standard form a plus bi, where a is a real number and bi is what's called the imaginary number. Sometimes you could use the real number 0. Most of the time, any type of imaginary number is also considered complex. We're going to go through plenty of examples of this. You need to know 4 things. Generally in class, I don't ask you to memorize things, but this is going to be one of those times where I do. So there are 4 types of imaginary numbers. First one is I to the first, and by definition, that's the square root of -1. I to the second is -1. I to the third is -I. I to the fourth is just 1. You have to know those. I write my I's with tails on them, just so they don't look like 1s. So I keep them separate. Generally, when we write imaginary numbers, we'll write like I, -1, -I, or 1. And I'll show you when we do examples. We don't write the square root of -1 for the final answer. So, what if I asked you to write each number as a product of a real number and I? Start with the square root of -25. If I were to ask you this example during a previous class, our calculator would have an error. or it would be outside of the domain. But using the imaginary numbers, we know that the square root of -1 just means I. So one thing we could do is write this, the square root of 25 times the square root of -1. Square root of 25 is 5, the square root of -1 is I. That would be the answer. I gave you the square root of -7. That's the same thing as the square root of 7 times the square root of -1. Can't do anything with the square root of 7, so we leave that alone. The square root of -1 is I. Generally, we put the I in front of the square root. That way it doesn't look like it's underneath it. What if we had the opposite of the square root of -81? Follow the rules. So square root of -81 we can't do, but we could do the square root of 81 times the square root of -1. Just breaking that up so we can work with it. Square root of 81 is 9. Square root of -1 is I. -9i would be that answer. The last type of problem like this would be if you had the square root of -44. This is the same thing as the square root of 44 times the square root of -1. Talked about how to do the square root of 44 before. I showed you a couple different ways. So you could either write this 2 times 22, which is 2 times 11, or think about the largest perfect root that goes into 44, which would be 4, right? No matter how you do this, this is like a problem we did on the last exam. You just have 2 square root of 11 times I, or 2i root 11. While you're copying this down, I just want to take a minute and mention i's are relevant to regular life. So, the other day, I took my first car to college. I bought it 19 years ago. It's a Camaro, and it's an older one. When I bought the car, when I was a sophomore in high school, I wanted to replace the sound system. And on the back of the speakers, I didn't know what I was doing at the time. I just took it apart and figured I'd go to the store and get upgraded components. On the back of the speaker, it said 2i. I had no idea what that meant. So I went, it was kind of like a PC Richards and Son, but they went out of business since then. But I went to the store and I said, this is the speaker that came out of my car. I want a better speaker to put in my car. And they gave me a speaker that was 4i. You have to write this down, actually. I put the 4i speaker in my car and it didn't sound as good. I did a little bit more research and I learned that the I is the imaginary number that we're talking about. So if anyone wants to be an engineer, or specifically an acoustics engineer, you're going to be learning about complex numbers. That affects how much sound comes out of the speaker. It actually is a measure of impedance of a speaker. So without getting all into it, impedance is how easily the speaker can move in and out. So the lower that I number, the more power you can get through the speaker. So I just think it's cool to talk about this because some of the things we do in class, you might think to yourself, when are we ever going to use this in real life? Especially for imaginary numbers. I mean, if you think about all of the stuff that we do in class, we're talking about imaginary numbers, but it is applicable to regular life. Yeah, so the question is, if you're online and you didn't hear, the term imaginary doesn't mean like an imaginary friend that somebody might have had when they were in first grade. It's not like a make-believe number. Imaginary just refers to taking the square root of a negative number. You could measure it. If you have, I think it's called a multimeter. It's a device that measures different types of electrical components. You could measure how much current is going through a circuit, how much the resistance is of that circuit. So imaginary doesn't have anything to do with make-believe. Just like complex doesn't mean what we would typically think it means, meaning hard. Complex just means something totally different, a combination of two separate things. Imaginary means the square root of a negative number. Does that make sense? One thing, I don't want to spend a whole lot of time in class going over this, but if you get a chance and you Google something that says fractal, fractals are beautiful. What they are is it's a pattern in geometry that uses imaginary numbers to create these incredible shapes. So you could make beautiful art using math, specifically using imaginary and complex numbers. So it's kind of a cool lesson. At the time, I thought complex numbers had to be the most useless thing that I'll ever learn, but after doing a little bit of research, it does have applications. So anyone else have questions or comments? All right. The next type of examples I wanted to do, I'll ask you just to multiply. Let's say if I was going to ask you to multiply the square root of -2 times the square root of -2. The answer isn't 4. This is not the square root of 4, which is not 2. That's totally wrong. Plus, you can't do this. If you type that into a calculator, you can't actually measure that. You can't measure this either. The way you have to do a problem like this is write square root of 2 times square root of -1 times the square root of 2 times the square root of -1. You have to break up each radical. If there's a negative inside a radical, you have to take it out and write I. So you're going to have square root of 2 times I times the square root of 2 times I. Square root of 2 times the square root of 2 is square root of 4. I times I is I squared. What did we say in the notes I squared was? -1. So this is just 2 times -1, or just -2. That's how you would do a problem like this. You have to break it up with imaginary numbers first. What about if we had the square root of -8 times the square root of -6? You can't just do -8 times -6 and get a positive answer. It doesn't work like that. You cannot multiply two radicals if both of the radicands are negative. So we have to do I. Step yet. I'm going to write the square root of -1 times the square root of 8 times the square root of -1 times the square root of 6, which is just I times I times the square root of 48. We just talked about I squared is -1. Figure out what the square root of 48 is, we could either use the technique of perfect squares, or we can make the prime factorization trick. I know that 2 goes into 48 24 times, 2 goes into 24 12 times, 2 goes into 12 6 times, 2 goes into 6 3 times. So remember, we're looking for groups of 2. We did this on the last test. So here's a group of 2, here's a group of 2, and there's a 3 left over. So we could write this -1 times 2 2 times 2 times the square root of 3, or this negative 4 root 3. Next, I wanted to talk about problems where we have to divide. So say if we had the square root of negative 80 divided by the square root of negative 5. You can't just combine the radicals. Remember what we said, if you have two radicals and both of them are negative, you can't combine them. You have to separate that negative somehow. I'm going to write this as square root of negative 1 times square root of 80 divided by the square root of negative 1 times the square root of 5. It's the same thing as with I divided by I, which cancels. Square root of 80 divided by square root of 5 is just the square root of 80 over 5. Cleaning this up a little bit, 80 over 5 is just 16. Or 16 is just 4. Recapping that, in order to multiply two radicals, if the radicands are negative, we have to take out the imaginary number by writing the I. Similarly, if you're dividing two imaginary numbers, we have to take out the I and then just use our properties of radicals. Want to do one more like this? What if we had the square root of negative 40 divided by the square root of 10? Both of those radicals aren't negative. So you're allowed to just do negative 40 divided by 10. Or if you just want to be consistent, anytime there's a negative inside, just take out the square root of negative 1. You don't have to do it here because both of those radicals aren't negative. You only have to do it if both of those radicals are negative. This just turns into I times the square root of 40 divided by 10. I times the square root of 4 is just 2. No problem with that. These are problems where we're simplifying radicals. I wanted to finish today by adding, subtracting, and multiplying with i's. So say we had a problem like this. I'll just ask you to simplify these. When I'm saying simplify, I mean by adding, subtracting, or multiplying. So generally, when we're working with algebra, we combine what are called like terms. That's really what simplified this means. It means combine like. So for the first example, if we have 2x plus 3 plus 3x minus 2, Like terms just means that they have the same variable and the same power. So 2x and the 3x would add to be 5x. 3 and negative 2 would add to be 1. But we all know how to do that. That's nothing new. What I'm going to do is I'm going to do the same thing with imaginary numbers. So say if we had negative 1 minus 8i plus 9 minus 3i. This is considered a complex number. Complex because the negative 1 is a real number and the 8i is imaginary. So it's not a hard problem to do. Generally, the way we get rid of parentheses is we just multiply the number that's on the outside. This would just be negative 1 minus 8i plus 9 minus 3i. Like I said, if there's parentheses, just multiply the number that's outside using the distributive property, and then we can combine like terms. The negative 1 and plus 9 just turns into 8. Negative 8i minus 3i is negative 11i. It's not really any harder than anything else we've been doing. Even if I were to make it a little bit longer. If I had negative 3 plus 2i plus 1 minus 3i plus negative 7 minus 5i. Because it's a longer problem doesn't mean it's any harder. If there's parentheses, we distribute the number outside the parentheses. In this case, it's just 1. And negative 3 plus 2i plus 1 minus 3i minus 7 minus 5i. Negative 3 plus 1 minus 7. Negative 2 minus 7 is negative 9. 2i minus 3i minus 5i is negative 6i. We could also subtract complex numbers. So say if we had negative 1 plus 2i minus 4 plus I. Be an example of subtracting. So just like before, there's parentheses, so we distribute the number in front. For the first grouping, it's 1. For the second grouping, it's negative 1. We get negative 1 plus 2i minus 4 minus I. Dividing my like terms is negative 5 plus I. We always convert the square root of negative 1 to I, but we never go from I to square root of negative 1. I is a good answer. That's an acceptable answer. We talked about how to add complex numbers. We talked about how to subtract complex numbers. Let's talk about how to multiply them. What if we had 6i times 4 plus 3i? We distribute. It's no different than anything else. Math is all about rules. Follow the rules. If it's using numbers, it's called arithmetic. If it's using letters, it's called algebra. If it's i's, it works exactly the same way. So 6i times 4 is 24i. 6i times 3i would be 18i to the second power. When you multiply I times I, it's like multiplying x times x. You add the exponents. What did you say I squared was? -1, right? So we could just write this 24I plus 18 times -1. And generally, when we're writing complex numbers, we put the I at the end. That's just standard form. We would write -18 plus 24I. Do one more of these. What if we had 6 minus 4I times 2 plus 3I? And just pretend the I is an X and everything else is exactly the same. In class, we talked about FOIL, a way to distribute. So first thing we do is we multiply the first terms. 6 times 2 is 12. We multiply the outer terms, which would be 6 times 3I is 18. Then we multiply the inner terms, which would be -8I. And then we multiply the last terms, which would be -12I squared. Forget, whenever you do I times I, you have to add the exponents. It's just 12. 18I minus 8I is 10I. And -12 times -1 is +12, which gives us 24 plus 10I as our final answer. Two more types of examples I want to go through with you tonight. I wanted to go through how to divide complex numbers and then how to simplify if I is a larger number. So let's take a look at this next group where we'll be dividing. And the first example is 3 over 2 plus I. What did we say I was? I is a square root, right? And remember, we talked about you're not allowed to have a square root in the denominator. So you have to come up with a way to get rid of this I in the denominator. If you don't write this down, but if you multiply by I, it's kind of like playing that whack-a-mole game at Chuck E. Cheese that we talked about before. You wind up with 3I over 2I plus I squared. So in an attempt to get rid of I over here, it just shows up somewhere else. So does anyone remember what we talked about when we have two terms in the denominator, one of them's a radical, or both are radicals? How do we get rid of it? We use something called the conjugate. And if you remember, conjugate just means you change the sign of that last term. So instead of having 2 plus I, we're going to multiply by 2 minus I. And using the conjugate as a way to get that radical to cancel out with the two middle terms. It's a pretty clever thing here. So if we go ahead and multiply, we don't care what goes on in the numerator. This would just be 6 minus 3I. In the denominator, we get 4 minus 2I plus 2I minus I squared. Just as it's supposed to, the i's cancel out. What did we say I squared was? -1, right? So we're subtracting -1. final answer would just be 6 minus 3i over 4 plus 1, which is 5. This would be what we do if there's two terms. There's just one term in the denominator, it's a little bit easier. Say if we had 3 plus I over 2i. You just want to get rid of the I in the denominator. So if it's just one term, you don't have to multiply by 2i. The 2 isn't a problem. The problem is the I. All you have to do is multiply the numerator and the denominator by I over itself. Plus, that'll make the denominator into I squared, which gets rid of the whole complex number. So on top, we just get 3i plus I squared divided by 2i squared. This is the same thing as 3i plus negative 1 over 2 times negative 1. And then just writing it in standard form, we put the I at the end. So negative 1 plus 3i over negative 2. That's good enough for me. Sometimes if there's a negative in the denominator, one thing we just do is divide that to the top. So you could also write 1 minus 3i over 2. We're just dividing everything on top by negative to take it out of the bottom. Both forms are totally fine with me. And then what I wanted to finish class with today, I want to show you how to simplify powers of different ways to do this, but from my experience, most people prefer to divide by 4, and the answer is I to the remainder power. I'll show you what I mean in a second. And just as reference for this, remember we talked about I to the first means the square root of negative 1. I to the second means negative 1. I to the third is negative I. And I to the fourth is 1. So we'll be referencing that as we go through these problems. For example, first example, what if I ask you what's I to the 12? So what we could do to do this is we do 12 divided by 4, which is 3 with a remainder of 0. 4 goes into 12 3 times, there's nothing left over. That remainder is going to be our answer power. Anything to the 0 power is just 1. If the remainder was 3, your answer would be I to the third. If If your answer was 2, your answer would be I to the second. Let me show you with another problem. What about if we had I to the 28th? Divided by 4 is 7, remainder of 0. Your answer again is just I to the 0. All right, let me come up with a different problem so we have a different remainder. What if we had I to the 31st? We do 31 divided by 4, which is it goes 7, right? It goes 7 times with a remainder of 3. Right? 31 over 4 is the same thing as 7 3/4. So your answer would just be I to the 3rd, which we said was negative I. That's how you do these kind of problems. One more of these. I just wanted to do a couple more different types to wrap things up here. What about if we had I to the 10th? What would be the remainder if we divided 10 by 4? It goes in twice with a remainder of 2, right? So you would say your answer is I to the 2nd, which we said was negative 1. I repeat every 4. So if we were to derive what I would have, this is just 5. The 6th is negative 1. The 7th is negative 5. 8. You can see it repeats every 4. That's why we are dividing by 4. To finish up tonight, what I wanted to do is to show you if there's negative exponents. So we'll begin then early here. What if we had I to the negative 9? Anyone remember what negative powers do? Yeah, this is the same thing as 1 over I to the 9. Well, I to the 9th, we just talked about how to handle. So in this case, let's figure out what I to the 9th simplifies to. 9 divided by 4, 2, with a remainder of 1. So we would write 1 over I to the 1st. But we talked about you can't have I in the denominator, right? So what would you do to get rid of it? Yeah, we multiply top and bottom by I like we did earlier. This is just I over I squared. We said I squared was negative 1. One more example. What about if we had I to the negative 22nd power? This will be our last one. Well, we know 1 over I to the 22nd. In order to simplify the denominator, we have to do 22 divided by 4, which is 5. We write this 1 over I to the 2nd, which is just 1 over negative 1, or negative 1 is our answer.